Finally, in our last video on alkynes, we'll be looking at reactions of alkynes. We're going to start with acid-base reactions, followed by alkylation, and then addition. But actually, we've already talked about acid-base reactions in terms of the properties of alkynes, and we talked about alkylation as a way to prepare larger alkynes from simpler alkynes. So I want you to think about acid-base reactions of alkynes both in terms of properties as well as reactions. And I want you to think of alkylation, or SN2 substitution of an alkyne anion. Think of that in terms of preparation as well as reactions. So in this video, we're going to focus on addition to the alkyne. In an earlier chapter, we spent a lot of time talking about addition to alkenes. Now we're going to see that many of those reactions have a similar reaction with alkynes. So we saw that an alkene can be reacted with hydrogen in the presence of a transition metal catalyst, such as palladium or platinum or nickel or rhodium. There's a lot of different ones that could be used. And hydrogen adds across the double bond, giving an alkane. Well, if we have an alkyne with a triple bond, can we add hydrogen to give an alkane, to give a cis alkene, or to give a trans alkene? And the answer is yes, we could do any of these depending on the reaction conditions. If we have an alkyne and we treat it with hydrogen gas in the presence of a good transition metal catalyst, then one equivalent of hydrogen is going to add to the alkyne, and it is a syn addition, so this gives the cis alkene as an intermediate, and then another equivalent of hydrogen will add another syn addition, and this will give the alkane. Now, the first addition is easier than the second addition. So if you have a really good catalyst, then you can do the first addition and it's good enough to do the second addition. But what if you have a not so good catalyst? So different poisoned catalysts have been developed, such as Lindlar's catalyst. Lindlar's catalyst involves palladium on calcium carbonate, but it is poisoned with lead and quinoline. Quinoline is this aromatic compound. We've got these rings. Right? This is Lindlar's catalyst. It's this combination of all of these. And so this effectively poisons the palladium. So instead of being a really good catalyst that's capable of catalyzing both the first addition and the second addition, this is only good enough to catalyze the first addition. And so we get syn addition because the alkyne will approach the surface of the metal, and so the hydrogens are going to add to the same face, resulting in the cis alkene, but this catalyst won't catalyze the second addition, and so you can get this to stop at the cis alkene. Now, if you tried to use a good catalyst and only use one equivalent of hydrogen, it's not necessarily going to stop at the alkene. You might have some alkyne converted to alkene, some alkene converted to alkane, some unreacted alkyne, some unreacted alkene, and the numbers just don't quite work out. It's not that every single molecule is converted to this, and then every single molecule is converted to this one. So just controlling the stoichiometry is not sufficient to control the product formation. You have to use a different catalyst to stop at the cis alkene. Now, this ability to make a cis alkene is also important because if we think about some of the ways that we learned how to make alkenes, such as a dehydration or dehydrohalogenation, the trans alkene would be the major product, and so this instead gives us a way to make the cis alkene. But what if we want the trans alkene? What if we start out with a small alkyne and we alkylate it, but then we want the trans alkene? Well, there is a different set of conditions, and this uses sodium metal along with liquid ammonia. and this is called a dissolving metal reduction. So this is sodium metal, or it could be done with lithium metal or potassium metal, but it's important to keep in mind we're talking about sodium metal in liquid ammonia, not sodium amide, where this is the sodium ion and NH2 minus. Okay, these are completely different reagents. So sodium in liquid ammonia, this will carry out a reduction converting the alkyne to a trans alkene. Now, this reaction has a pretty complicated mechanism. It involves an electron transfer to give an anion radical, followed by proton transfer, followed by another electron transfer, followed by another proton transfer. You're not responsible for the mechanism. If you're interested, it is described in your textbook or in any organic chemistry textbook, so you can find out about it if you're interested. I want you to be able to know what happens. I'm not going to ask you about how it happens. So, alkynes can be converted to alkanes, or they can be converted selectively to cis alkenes, or they can be converted selectively to trans alkenes, depending on the reaction conditions. Next, let's take a look at the addition of HX to alkynes. But first of all, let's remember that we saw the addition of HX to an alkene. And in this case, what we saw was that the hydrogen added to the carbon that originally had more hydrogens, the bromine added to the carbon that had fewer hydrogens, resulting in this product, which is the result of Markovnikov addition. And remember, the reason is because of the mechanism where the alkene shares its electrons with the hydrogen, kicking out the bromine, and a carbocation is generated. The more stable carbocation would be at this position, not at this position. And so this one is the carbocation in the intermediate, and then the bromine adds here. Now, the addition of HX to an alkyne is similar, not exactly the same mechanism, but it's helpful to keep in mind the alkene mechanism because that will help you to predict the regioselectivity of the alkyne addition. So if we have an alkyne and we treat it with an HX, such as HBr, if we have just one equivalent, then we are going to get an alkene where we've added the hydrogen to this alkyne carbon and we've added the bromine to the more substituted alkyne carbon. So once again, we have Markovnikov addition. The hydrogen adds here, the bromine adds here. We still have an alkene. And this reaction works with HBr, HCl, HI. Now, if we use two equivalents, or we might just say that we have an excess of the HBr, then a second equivalent will add, and that would give us this product. So we've added H and Br twice across the alkyne. Both of them are Markovnikov addition. So we don't have to do one addition, isolate it, and then add a second. If we just added excess HBr, then we would get the dihalide. Next, let's consider the addition of water. So with alkenes, we saw that we could carry out an acid-catalyzed hydration, and this would result in Markovnikov addition of hydrogen and the OH across the double bond. With an alkyne, rather than doing an acid-catalyzed hydration, you can use an acid-catalyzed hydration in the presence of a mercury salt. So this is really kind of like an oxymercuration demercuration, which was another example, which was another reaction that we talked about with alkenes as an alternative way to get Markovnikov addition of water. So with an alkyne, you can call this acid catalyzed hydration with mercury, you can call this an oxymercuration, and we get a ketone as our product. What's going on? So just like we saw with an alkene, we can have H and OH add across an alkyne. And what that will give us, in this case, it is an internal alkyne. So Markovnikov addition isn't relevant. If the OH adds here and the H adds here, then we get this, which is called an enol. Now, an enol can tautomerize to give a ketone. Notice we have the same connectivity among the carbons and the oxygen. The hydrogen was on the oxygen. Now we have an extra hydrogen here. We had a single bond between the CO, a double bond between the CC. Here, double bond between the CO, single bond between the CC. So in general, an enol is a less stable isomer than the ketone. And so under acidic conditions, which is what we have here, the enol will automatically tautomerize to give the ketone. Tautomerize, this is a fancy word for an isomerization between two tautomers. And tautomers have the same connectivity with the heavy atoms. It's just a difference in the location of the hydrogens and the bonds. So this is a pair of tautomers. So when this isomerizes to this, it's called a tautomerization. Now, what if we don't have a symmetric alkyne? What if we have an unsymmetric alkyne? Well, just like we saw with alkenes, we will get Markovnikov addition. So the hydrogen will add to this alkyne carbon and the OH will add to this carbon, giving this enol, not this one. Okay, we get the Markovnikov enol, which then tautomerizes to give the ketone. So if you're interested in the mechanism of a tautomerization, we can talk about that. You can look it up. I'm not going to ask you about that, but I still think it is helpful to consider the enol just because this way it's easier to remember Markovnikov addition. The hydrogen adds here, the OH adds here, giving this. When we looked at addition of water to alkenes, we saw that we could also do a hydroboration oxidation to add H and OH across the double bond, but this time it proceeded with non-Markovnikov or anti-Markovnikov addition. So when using hydroboration oxidation, so BH3 and THF, or it might be diborane B2H6, followed by hydrogen peroxide and hydroxide. This is the hydroboration step, followed by the oxidation step. And this gives us non-Markovnikov syn addition. We can carry out an analogous reaction with an alkyne. We could potentially use the same conditions, and this will add H and OH, giving the enol. The enol will tautomerize to give the ketone. Now, when you carry out hydroboration oxidation on an alkyne, you might see borane and THF or diborane, the same as what we saw for alkenes, or we might see other types of boron reagents. One common one is called dicyamylborane, and here we have this group connected to the boron. Sometimes using borane will lead to double addition to the alkyne, so rather than using that, the dicyamylborane or some other big bulky borane will be used instead. So just recognize this if you see this term, but mainly focus on the boron followed by the oxidation. So hydroboration, oxidation. This gives non-Markovnikov addition, which means the hydrogen adds to this carbon and the OH adds to this carbon, giving this enol. And notice this is the opposite regiochemistry compared to what we saw on the previous slide. Now, when this enol tautomerizes, we get the aldehyde rather than the ketone. So non-Markovnikov addition to a terminal alkyne results in the preparation of an aldehyde. Another reaction that we saw with alkenes was the addition of X2 across the double bond. This resulted in anti-addition. This goes through the formation of a cyclic bromonium ion, followed by attack of the second bromine coming from the opposite face, which gives you the trans relationship between the bromines or the chlorines or whatever is being used. If we have an alkyne and we are treating it with bromine, if we add just a single equivalent, then we are going to get this, where we still have the alkene. And in general, but not always, but generally, we get trans addition. Remember, Markovnikov addition is irrelevant because we're adding bromine and bromine. Rather than using one equivalent, if we use two equivalents, then we can add bromine across the triple bond twice. So in this case, we are going to get a dibromide on this carbon and a dibromide on this carbon, giving us 1122 tetrabromo propane. For the addition of a halogen to an alkyne, the mechanism is similar to what we saw with addition to an alkene, but not exactly the same. In general, if we add one equivalent, we will get the trans dibromide, and then if we add two equivalents, well, we end up with the tetrabromide. Finally, let's see if we can put this all together. Can we carry out preparation and reactions of alkynes to do a multi-step synthesis to give us a target compound? Looking at our first example, we have a 4-carbon chain and we're ending with a 4-carbon chain, so we don't have to make any carbon-carbon bonds. We're starting out with an alcohol and we end up with an alkene. So this is just a nice, easy functional group transformation. But if we have our alcohol and we treat it with strong acid, heat it up to carry out a dehydration, we are going to get the trans alkene. Yes, we're going to get a little bit of cis, but that's not going to be our major product. Making the cis alkene, it's going to take a few more steps. If we want to make a cis alkene, the only way that we know how to do this is to have an alkyne and carry out a reduction using Lindlar's catalyst. So we need to figure out, how do we make an alkyne? We can still convert the alcohol to an alkene. We'll have a mixture of mostly trans, but also some cis. We can add bromine or chlorine, and this will add across the double bond. I'm not really trying to show stereochemistry. We're going to get a dibromide. Now that we have a vicinal dibromide, we can treat this with an excess of sodium amide. Remember, we've got the NH2 minus, very strong base. This will do a double dehydrohalogenation to give the alkyne. And then once we have the alkyne, this is where we can carry out the reduction using hydrogen and Lindlar's catalyst to give the cis alkene. So going from an alcohol to a trans alkene can be done in one step. Going to the cis alkene, we need 1, 2, 3, 4 steps. Looking at our next example, we're starting out with only 3 carbons. We have a dibromide. Our target has 5 carbons, so we know that we have to make a carbon-carbon double bond. And for this particular example, we can obtain our target as a mixture of stereoisomers. That's okay. So starting out with 3 carbons, we need to get to 5. So the only way that we know how to make carbon-carbon bonds is an alkyne alkylation. So we need an alkyne. So if we take our dibromide and we treat this with the sodium amide, we need an excess that will allow us to make the alkyne. Now we can treat this with another equivalent of sodium amide or another really strong base, followed by we need CH3CH2Br or Cl or I, because that's going to give us, after our SN2 reaction, I'm going to write this out now. We have our CH3 connected to our alkyne carbon, connected to our other alkyne carbon, which is now connected to the CH2, CH3. So this was an SN2 substitution where the bromide was kicked out, and now we have our 5-carbon chain that we need. Now, how do we convert an alkyne to the dibromide? There are actually a few different ways that we could do this. We could, for example, treat this with hydrogen and Lindlar's catalyst, and that will give us the cis alkene. Or we could do sodium metal and ammonia, and that would give us the trans alkene. And then either one of these could be treated with bromine to give the dibromide. This is going to give a different stereochemical relationship. So bromine and a bromine. All right, so these will be different, but it's an approach that can be used. Alternatively, we could treat our alkyne with one equivalent of bromine to get primarily the trans alkene with the dibromide, and then we can treat this with hydrogen and palladium to reduce the double bond, giving us the dibromide. So a few different approaches are possible. If you see a cis alkene, we need to keep in mind that the only way we know how to do that is using an alkyne. If we have a starting material compared to a product, the product has more carbons, then we know that we need to think about alkylating an alkyne. Once we have our alkyne, there might be multiple ways, there might be different ways to get from our intermediate to our target. If the particular stereoisomers did make a difference, then we would have to think more closely about the resulting stereochemistry from these 3 different approaches. So this wraps up what we're looking at regarding alkynes. I want you to keep practicing with preparation of alkynes and keep practicing with reactions of alkynes so that you can begin to think about multi-step synthesis.